Welcome back, everybody. Today we are starting our new unit, so another really, the quadratic unit was kind of long. This is a really brief unit in comparison. I think we only have like 4 lessons before we're taking another quiz. Anyway, it's important, but definitely connected to what we were doing in our quadratic unit. So it's a unit about polynomials. Polynomials are just collections of terms where you can't have any negative exponents. Technically, quadratics are polynomials. They're just polynomials with a degree of 2, right? Polynomials with a degree of 1 are linear, polynomials with a degree of 3 are cubic. So we've looked at some subsets of polynomials, but if we just have a blanket category of polynomials, there are some features that we have to know about. And I'm going to try to connect some of the dots today. So today we're going to talk about division of polynomials, and then what that means in terms of factors and how factors are important for roots. And remember, roots, which we mentioned before, are another name for the x-intercepts of a graph, okay? So we're going to see how all these things are related. So we're going to start with dividing polynomials, and we've seen some of this before. If we wanted to divide, like this first one, 18x cubed minus 6x squared plus 12x by 3x, when our divisor is only one term, so the divisor, remember here, this is what we call the dividend, and then this is what we call the divisor. The divisor is the one that does the dividing. When the divisor is only one term, that's the stipulation here, when the divisor is one term, we can use the quotient rule. So the quotient rule might be easier if you saw it like this. If we took 18x cubed minus 6x squared plus 12x, and I said divide it by 3x this way, we are literally just dividing each of these terms by 3x. Okay, it's like reducing the whole fraction by 3x. We can only do this when we have a single term in our divisor. So we end up with, this is the same as dividing each of these separately. 18x cubed divided by 3x is going to be a 6 with an x squared. Negative 6 divided by 3 is going to be negative 2. And then the square here minus the 1 here leaves us x to the first. And then 12 divided by 3 is 4. And then 1 minus 1 will leave us no x's. So this is going to be our, 4 here. This is, let me change the color. So this is called the dividend. And we've talked about these words before somewhere. This was called the quotient. The answer is called the quotient. Okay? And that's it. Again, we can use this quotient rule. The quotient rule says to divide the coefficients and subtract the exponents. Okay, so that's what we're going to use if our divisor is a single term. That'd be best case scenario because that's pretty simple. Now, we also have looked before at long division. We said if the if the divisor was not a single term, we would have to use long division to divide. And I could try to write this the same way. Don't write this on yours yet because it's not what we're going to do. But if I tried to write it like this, we could try to see if the top is factorable. Are there going to be factors of negative 8 that make 3? No, like if this factored into a 2x plus 1 and let's say an x minus 4, then no big deal, but that's not the case here. So since I can't factor and I can't divide by 2 terms on the bottom, we're going to have to use long division here. So we can use long division when the divisor has more than one term. So when the divisor has more than one term, we're going to try this long division. And we've done this before, so this is really just to dust off the cobwebs. Remember, our divisor, 2x plus 1, goes outside of the box. Dividend goes in the box, so 2x squared plus 3x minus 4. And when we start the division, we are looking at just the first term divided by the first term. So we're just going to be dividing the 2x squared by the 2x. And what is 2x squared divided by 2x? Is going to be 1x. So that's the first part of the quotient. The answer goes on top of the box. Now remember, with division, we divide just the first term by the first term. But now we're ready to do the multiply step. And when we multiply, it's by the whole divisor. So we multiply here. X times 2x is 2x squared. And x times 1 is 1x. So now we divided, we multiplied, and next step is, do you remember? It's subtract. So I gotta subtract. I'm gonna draw my line here, subtract this, subtract that. 2x squared minus 2x squared makes these cancel, and 3x minus the 1x leaves me with 2x here, and then we bring down the next term, and we do that again. So we're taking our, taking our first term and dividing by our first term. So 2x divided by 2x. And on the side here, oops, let me get rid of my highlight. 2x divided by 2x is just going to be 1. So a positive 1 is the next part of my quotient. And then I'm going to multiply it. 2x times 1 makes 2x. And 1 times 1 makes 1. Now I have to subtract that. Get rid of this mess I'm making everywhere. I got to subtract that. So I'm going to draw my line here. Subtract that, subtract that. 2x minus 2x cancels. And negative 4 minus the 1 gives me a negative 5 here. And since there's nothing left to bring down, that makes negative 5 the remainder. So remember how to write this. We're going to say this answer is x plus 1. And then because it's a negative remainder, we're going to say minus. And the remainder, 5, goes over the divisor, which was 2x plus 1. So that would be our answer here. Okay? So we have notes on this somewhere. I can't remember the section that it's in, but if you look back through your notes, we did talk about long division. Why can't I remember where we did it? Oblique asymptotes, that's what it was. It's in our rational unit, okay? So remember, basically the 3 key steps were to divide, and then multiply, and then subtract, and you just kind of kept repeating that process until you got to your remainder. So remember, the remainder goes over the divisor, the division only uses the first terms, and the multiplication uses the whole divisor, okay? Now, I might have mentioned this when we did the oblique asymptotes, but there is a shortcut to long division. And I didn't show it to you before because it doesn't apply to every problem, but because we're going to be using this a lot, we want to be able to take a shortcut if we can. So synthetic division is a shortcut, but it only works when the divisor is of a certain form. If you look at the divisor here, our divisor has to be of the form x plus or minus c. That means you can have x plus a number, or you can have x minus a number, but the coefficient of x has to be a 1, and the exponent of x has to be a 1. So you have to be dividing by 1x plus or minus whatever, doesn't matter. So if your divisor looks like that, then we can use synthetic division. This is a shortcut. So synthetic division is a shortcut. What it does is it takes the variables out of the long division process, and the variables in that process are what make that look a little complicated. Now, to try to make this make sense to you, I'm going to show you my scratch paper here, okay? So let's say we were going to divide x plus 2 into something like 3x squared plus 2x minus 1, okay? Right now, the only method we know is, or maybe remember, is the long division. That's the one we just recapped. So if I was going to use long division, it's good for you to see it again, I'm going to start by dividing my first term by my first term. So 3x squared gets divided by x, and that leaves me a 3 and an x. So 3x goes here, and then I multiply. 3x times x is 3x squared. 3x times 2 is going to give me a positive 6x. Now I gotta subtract, so I'm gonna subtract these will cancel. 2 minus the 6 is gonna leave me a negative 4x. I'm gonna bring down my minus 1 and do it again. First term divided by first term. So negative 4x divided by x gives me a negative 4. So negative 4 is gonna go up here. I'm gonna multiply. Negative 4 times x is negative 4x. Negative 4 times 2 is a negative 8. I gotta subtract, so I'm gonna draw my line here. Subtract, subtract, double negatives make these positives. So those will cancel, and then negative 1 and positive 8 makes my remainder 7. So I end up with 3x minus 4 plus 7 over x plus 2. Okay? So synthetic division can shortcut that. And wouldn't a shortcut for all that be lovely? It can shortcut this particular problem because my divisor is of the form that's required, where I have 1x to the first power, okay? So with the synthetic division, what we do is eliminate the variables. So let's look at this original problem here. This original problem right here. If I got rid of the variables from that problem, how would this look? Well, I would still have a 2, and then I would have a 3, and then a 2, and then a -1, right? Now I know there's a 1 in front of the x here, but I'm not going to worry about that. So I would be looking at a 2, a 3, a 2, and a -1. So if all the variables are gone, that's what I'd be dealing with, right? So it would look like this, okay? Now with synthetic division, you'll see why in a minute, we turn the division box upside down. So instead of making my box go this way, I'm going to make my box go the other way, okay? Now what happens? Well, when I go to divide my first term here by my first term here by my first term here, because the number I'm dividing by is 1, whatever this number is, the coefficient of this x squared, or whatever it is, it's got to be the same number here. So if it's 3x squared divided by 1x, I'm going to get a 3x here. If it was 5x squared divided by 1x, I would get a 5x here. So this number here is always the first part of my answer. So we're going to say, let's just bring this number down. Right under the box now is going to be my answer instead of on top of the box. So the first part of my answer is going to have a 3 in it. Okay? Now, what did we do with the 3 up here? We multiplied, right? So that's what I'm going to do. I'm going to take the 3 that's here and multiply by the 2. So 3 times 2 is 6. And see where the 6 is here? It's in the work. So I'm going to put that here in the work. Now, what happened with the 2 and the 6? We had to subtract that. So if I subtract the 2 and the 6, I get the next part of my answer, which was -4, right? The next part of my answer. And then I took the -4 and I multiplied it. So -4 times 2 would give me a -8. And we can see that here. I've got the -1 and the -8. And then I had to subtract that. And 1 minus a -8 became 1 plus 8, which gave me the 7. And notice I've got the 3, the 4, and the 7. The 3, the 4, and the 7, the same things I had there. I just now have to figure out what's what. So I've got to put the variables back in. So if we start with an x squared and we divide by an x, then our answer starts 1 degree less, right? I take 2 x's, divide 1 out, I start with an x to the first. If I had started with an x cubed and I divided by an x to the first, then I'd have an x squared. So this degree of your answer should always be 1 degree less than what you started with here. So if I started with an x squared, then when I go to put my variables back in, I start with an x to the first. And then you would just descend down. Well, descending down means you'd have, like if you started with x squared, then it'd be x to the first, then x to the 0, but what's anything to the power of 0? It's just 1. So x to the first will be the last of the variables, and then it would be the constant, and then the last number is going to be the remainder. So we have x to the first, this is our constant, and this last one is going to be the remainder. So we're reading this as 3x minus 4 plus a remainder of 7 over the divisor, which was x plus 2. Okay? Now let me just show it to you again without this nonsense everywhere on the paper. So if we had, give me another one here, x plus 3, and let's say we were dividing into 4x squared minus x plus 5 or something, okay? So we're going to take the 3, and then we're going to put here the 4, the -1, and the 5. And I know that this is going to be the first number in my answer, so I'm just going to bring it down. And then we multiply, we get 12. If we subtract that, we get -13. Multiply, we get -39. If we subtract that, that becomes a plus, and we end up with 44 here. So this started with an x squared, that means this starts with an x to the first, this is the constant, and this is the remainder. Okay, so then our answer would be 4x minus 13 plus a remainder of 44 over the divisor, which was x plus 3. Okay, now, just to make this a little bit more foolproof, the mistakes that happen here, and in the long division also, the mistakes happen here in the subtracting process, right? Subtracting is in my opinion, much more difficult than adding because we just make more sign mistakes. So the creator of this synthetic division process said, well, instead of having to subtract here and subtract here, subtract all the way across, which basically just changes the signs of our numbers, instead of changing all of these signs, let's just change this sign. Okay, so that instead of subtracting here, we can add, right? Let me show that to you again. So what we're going to do is instead of subtracting, we're going to change one sign here, and then we're going to add. So if this is a plus 3, I'm going to put a minus 3 out here, and I'm going to leave my 4 and my negative 1 and 5, but because I changed this sign, now it's going to be a multiply and add. So 4 comes down, I multiply to get negative 12, I'm going to add these to make negative 13. Multiply to get positive 39, and then add these to get 44. Same answer, but adding is easier than subtracting. Okay, so that is synthetic division. You're going to take the opposite of this number. It's going to go outside of an upside down box, fill in your coefficients, bring the first one down, and then multiply and add all the way across. Okay, let me show you here. I don't know space for steps, but here we go. So I'm going to put the opposite of negative 3, which is positive 3, outside of this upside down box. I'm going to put in my coefficients 3, 1, and negative 5. 1 and negative 5. Bring down the first number, and then we're going to be multiplying here, multiply here, and then we're going to be adding in here till we get to the end. Okay, so bring the first number down, multiply 3 times 3 to make 9, add the 1 and the 9 to make 10, multiply the 3 and the 10 to make 30, and add these two to make 25. And now we have it. Now we just put the variables back in. So since we started with an x squared, this starts with an x to the first, and then that's a plus 10, and this is a plus 25 is my remainder, which goes over my divisor, x minus 3. And there it is. A lot faster than long division. Okay? Let's try it again. So x plus 1, I'm going to put the opposite of this number, negative 1, outside of my box. And then inside, 2, negative 5, negative 1, and 4. And then we bring this down, and then multiply and add. So negative 1 times 2 is negative 2. We add these to get negative 7. Multiply negative 1, negative 7 to make 7. Add negative 1 and 7 to get 6. Multiply negative 1 and 6 to get negative 6, and then add here to make negative 2. So this time we started with an x to the third, which means our answer will start with an x squared. And then this will be x to the first, this will be our constant, and this will be our remainder. So let me just do this on the side here. Oops. So this is 2x squared minus 7x to the first, plus a constant of 6 minus a remainder of 2 over our divisor x plus 1. So this second to last number is always the constant, and the last number is always the remainder. Okay, now I want to show you one more. You got to be careful if there are terms missing in the process. I don't know if we saw this with long division, but so you see how here it goes from 8x cubed just to the constant. There's no x squared term, there's no x to the first term, it just jumps to the constant. Things get a little out of whack. I could show you, but I don't want this video to be an hour long. But if there are terms missing, we're going to have to put zeros in to hold those places. So outside of the box is going to go a negative 5, and then inside the box we're going to put the 8, 0x squared, 0x to the first, and then my 125. So this comes down, we multiply, we get negative 40, add, we get negative 40, multiply, that's 200, add, that's 200, multiply, we get a negative 1,000, and then add, we get a negative 875. And we started with a cube, divided that down, so now we have 8x squared minus 40x plus 200, and then minus 875 is my remainder over the divisor, which was x plus 5. Okay, so I like that a lot better than the long division, but remember you can only use that if our divisor is of the right form. Okay, so why is it important? well, what does all this mean? Why do we need division and such? We're going to try to connect, okay? So the connection between division and where we're going is factors. If there's no remainder when you divide two polynomials, that means the divisor divides evenly. It means it divides evenly into the dividend, right? If there's no remainder, it divided evenly. And why is that important? Well, if there's no remainder and it divides evenly, or if it divides evenly, it's a factor. Okay, let me take this back to just some normal numbers for you. If I said 28 divided by 8 was exactly 3, that means that 8 is a factor of 24, right? Because 8 divides evenly in exactly 3 times. Also, it means that if I was to remultiply the 8 and the 3, it would take me back to 24, okay? The same is true for polynomials. If I took some polynomial, like 8x cubed plus 125, and I divided it by another polynomial, and it divided exactly into this with no remainder, that means that the 2x plus 5 was a factor of the 8x cubed plus 125. And it also means that I could multiply these two to get back to that original polynomial, okay? So let me show you what you should be able to do with this information. If I asked you this question, did I get my bullet points there? Yeah, if I asked you this question, is 2x plus 3 a factor of 2x cubed plus 5x squared minus 23x minus 12? How do you answer? Well, in the past when we talked about factors, we talked about factoring, right? Like if I said to factor, if I said to factor 2x, if I said to factor x squared plus 3x plus 2, then it would factor into x plus 2 and x plus 1, which means x plus 2 is a factor, x plus 1 is a factor, right? Well, if I said is 2x plus 3 a factor of this big polynomial here, maybe we could try to factor, right? But how do we factor when we have 4 terms? Well, 4 terms, we use grouping. If I try to factor this by grouping, the first group I could take out an x squared, which would leave me at 2x plus 5. What about the second group? Nothing in common, right? It means this thing isn't factorable by grouping, so we could not use that process to determine if 2x plus 3 was a factor. Now, just because we can't factor by grouping doesn't mean that this polynomial doesn't have factors. It just means it can't be factored using one of our traditional methods, okay? So if I want to know if this is a factor, I can use division. If 2x plus 3 is a factor of this polynomial, it will divide evenly into it. So I'm going to use division. Now, what kind of division do I have to use? Well, I have to use long division because the coefficient of x is not a 1, it's a 2. So I'm going to go 2x plus 3 into 2x cubed 5x squared minus 23x minus 12. Okay, so first term divided by first term. 2x cubed divided by 2x is going to be x squared. That goes here. X squared times 2x is 2x cubed. X squared times 3 is 3x squared. If I go to subtract, these are going to cancel. 5 minus 3 is going to leave me with 2x squared. I'm going to bring down my minus 23x and do that again. First term divided by first term. This time it's 2x squared divided by 2x, so I get nx. So plus x here. X times 2x is 2x squared. X times 3 is 3x. Gotta subtract. So subtract, those cancel. Negative 23x minus 3x is going to give me negative 26x. Bring down my next term and go one more time. This time negative 26x divided by 2x is going to give me a negative 13. So minus 13 here. Multiply, it's negative 26x and negative 39. And then subtract one last time here. Minus makes these double negatives positives. So those will cancel, and the 39 minus the 12 leaves me with 27 as in my remainder. So the remainder here, this remainder tells me that this thing does not divide evenly, right? If it doesn't divide evenly, that means 2x plus 3 is not a factor. So we're going to say no, because, it's right, if we're justifying here, it doesn't divide evenly. Doesn't divide evenly. All right, there's a remainder when we divide. Okay, now let's try again. Is x plus 3 a factor of that polynomial? Again, not going to be factorable using our grouping method. Doesn't mean that it doesn't have factors, it just means we can't use that traditional method. So we're going to use division here and try to figure this out. Now this is a candidate for synthetic division because our divisor is of the right form, 1x to the first. So I'm going to put a minus 3 outside of the box, and then inside of the box, 1x cubed, 2x squared, negative 5x, and a constant of negative 6. Let's bring this down. Multiply, add, multiply to get 3, add to get negative 2, multiply to get 6, add, and we get 0. That 0 right there means we have no remainder. If there is no remainder when we divide, that means x plus 3 is in fact a factor of that polynomial. So yes, it divides evenly. Okay? Now, if it divides evenly, then we can use that to rewrite this thing in factored form. So this polynomial in number 3, this is the same polynomial that we had in number 2. Remember what we said earlier. If I said that 24 divided by 8 was exactly 3, that means I could multiply 3 and 8 to get back to 24, right? So think about what we just said here. We said that x cubed plus 2x squared minus 5x minus 6 divided by x plus 3 was exactly, from our answer here, 1x squared minus 1x minus 2, right? 1x squared minus x minus 2, which means, just like here, 24 divides by 8 exactly 3 times. That means I could multiply these two to get back to this. So that means the product of these two things has to equal this. So we could say that this polynomial is equal to x plus 3 times x squared minus x minus 2. That would be the factored form of that equation. Okay, so that would be the factored form of that equation. So this, not the traditional way to factor a polynomial of 4 terms, but this is one way we could do it, okay? Now, why is that important? Why do we need to be able to identify factors of polynomials? So let's take calculator, not what I wanted. Let's take this to the next step, okay? Why are factors of polynomials important? Typo. Polynomials. Why are factors important? So if we were looking at a polynomial expression, right, no equal sign, just an expression in factored form, x squared plus 5x plus 4 doesn't really do much for us. But if we took that same expression and made it an equation, well, the equation in factored form is much more helpful because that factored form shows me the solutions. I can tell right away -1 and -4 solutions. I can't see that here, right? That standard form doesn't show me anything, but here, right, my factored form tells me the solutions. And then if I took that equation and looked at it as a function, again, the function in the standard form, while it tells me where it's going to cross the y-axis, this form is more important because it shows me exactly where the roots are going to be. So I have roots, right, at -1, 0, and a root at -4, 0. So the factors are important because the factors, right, the x plus 1, the x plus 4, they show us the solutions to our equations, and they show us the roots to our functions. Okay, so the factors are important. They give us all kinds of information. Get rid of all my scribbles here. All right, factors, super important. Factors reveal the solutions to our polynomial equations. Now, I showed you quadratic here, but it's going to be true for any polynomial. And they also show us the roots, which are also called x-intercepts, of the related polynomial functions, okay? So the factors are important because they show us solutions and they show us roots. Solutions if it's the equation, or roots if it's the function. So again, what kinds of questions could I ask you based on that information? Well, I could say, for number 4, to identify all the roots for this function. Now it's a function, you could definitely put it in Desmos and graph it and see where it's crossing the x-axis, but because it's in factored form, you should be able to quickly identify the solutions or the roots. So what would zero all of these things out? This one tells me 0 is going to be a solution. So maybe 2 steps here. This one tells me 0 would be a solution. This tells me 7 would be a solution. This tells me -2 would be a solution. And this tells me -1/3 would be a solution. That means we would have a root at 0, 0, a root at 7, 0, a root at -2, 0, and a root at -1/3 and 0. Okay? So without even having to go into Desmos, I can see the roots that are happening there. Okay? Now, I can also do something like number 5. It says to write the following polynomial in factored form. Again, this is a 4-term polynomial, but I would not be able to factor this using grouping. So what do I do? Well, this one I'm going to actually go to Desmos. If I put this in Desmos, we are looking at y equals 5x to the 3rd power plus, really slow because this keyboard is tiny and my fingers are too big, sorry, 18x to the 2nd minus 11x, and then minus 12. We see that this graph crosses the x-axis 3 times. So I graphed this. Oh my goodness. Oh, work with me here, paper. Work with me. Oh my goodness. Okay. Bear with me, people. I'm so sorry. So I graphed this and found roots at, I have a root here at -4, 0, and a root here at -0.6. Now, -0.6, I don't want the decimal there, so I'm going to make that a fraction. So I got -3/5, and then the last one here is at 1. Okay, so what we're doing here is going in reverse of the last one, right? This one's already in factored form, so I could identify the roots. Well, now I can identify the roots and then use those to write my factored form. This means that f of x has to be equal to, if -4 is a root, it means that x plus 4 is a factor. Okay? If -3/5 is a root, it means that 5x plus 3, remember opposites, has to be a factor. If, another color here, 1 is a root, then x minus 1 has to be a factor. Okay? So we work in reverse, right? If we know the roots, we can find the factors. If we have the factors, then we can find the roots, all right? And maybe a little Desmos along the way. Now there's a couple more things that you need to know about roots. First, I think this one we know based on solving equations from before, but the total, right? The total number of solutions for an equation or roots for a function is determined by the degree. So a 3rd degree, like we have here, right, is going to have 3 factors, 3 roots, 3 solutions if it were an equation. If it was a degree of 4, we'd have 4, a degree of 7 would be 7, and so on. And then there's certain kinds of roots that come in pairs. Certain kinds of roots that come in pairs. Let me go back to my scratch paper here. What kinds of roots come in pairs? So let's say your equation was x squared equal to 5 here. To solve this, you'd have to square root both sides, and so you end up with this irrational solution. Well, when we square root, we always put in the plus or minus in front of that square root. So anytime you have an irrational solution, it came from taking the square root in that solving process, so you're always going to have the plus or minus in front of it. So irrational solutions like this they come in pairs. They have to. There's always going to be a plus or minus in front of that square root. So if you were told that only, let's say, radical 3 was an answer, or if you were told radical 3 was an answer, then we automatically know negative radical 3 would have to be an answer too. Okay, now that's true not just for irrational, it's also true for imaginary. So if this was, let's say, x squared equal to a negative 4, when I go to square root this, again, x is going to be equal to, it has to be a plus or minus, and then a 2i. So imaginary solutions, the same thing happens, right? When you go to square root that negative, there's going to be a plus or minus that goes in front of that 2i. And that's true for complex as well, right? If you had like x minus 3 squared equal to a negative 4. When you go to square root here, you got x minus 3 equal to plus or minus 2i, right? And then you got to add that 3 over. So 3 plus or minus 2i, both solutions, two complex solutions. So there's no way an equation could have an odd number of either irrational, imaginary, or complex solutions. They always come in pairs, okay? So all irrational, all complex, all imaginary solutions come, or roots, come in pairs. They have to. So you could be asked a question like this one. Let's say you have a polynomial function of degree 3, and you know two of the roots are at 3 and at 2i. What does that last root have to be? There has to be 3 roots if it's degree of 3. Well, the last root has to be the one that's paired up with this one, right? X equals negative 2i would have to be the third root, because imaginaries come in pairs, okay? Now we've got a degree of 7, so we've got 1, 2, 3, 4 solutions. What are the remaining 3? The pair of this, 1 minus 4i. The pair this would be a positive 2i, and the pair with this would be a positive radical 2. So they're your remaining 3 roots. So 3 remaining here, and there would be 1 remaining here. Okay. Also, it could be asked to write a polynomial function of degree 3 in factored form. So if x equals 1 and x equals a radical 5, then we know we have a third root. X is also going to be equal to a negative radical 5. So we could write a function like f of x in factored form. We could say if positive 1 is a root, that x minus 1 is a factor. If radical 5 is a root, we can say x minus radical 5 is a factor. And if negative radical 5 is a root, we could say x plus radical 5 is a factor. Okay? So there's your factored form. Now, in the next one it says standard form. This was factored form. Now it's write a function of degree 3. This would be an equation of degree 3, but this time in standard form. Now we're going to start the same way. We have a partner here. If 2 radical 3 is a solution, so is negative 2 radical 3. So in factored form, this is an equation this time, not a function. So if negative 4 is an answer, x plus 4 is a factor. If 2 radical 3 is an answer, x minus 2 radical 3 is a factor. And then lastly, x plus 2 radical 3 is a factor. And we're going to make this all equal 0 now because it's an equation. And then because it's in standard form, we need to multiply it out. Now it doesn't matter the order you multiply, but I would definitely start with the conjugates. So x times x is going to give me an x squared here. And I know that this will cancel with this. So I'm going to skip to here, where we get a negative 4 radical 9. So we end up with x squared minus 4 times 3, which is x squared minus 12. Okay, so we get an x squared minus 12 there. We still have to multiply by an x plus 4, but this won't be so bad. Okay, so one more step here, and I'm running a little tight on space. I'm sure the same is happening to you. See if I can squeeze this in. So x times x is going to be x cubed. X times negative 12 is a negative 12x. Here we get a positive 4x squared. and then at the end here, a negative 48, all equal to 0. And just so I can put that in the proper form, proper order, we're going to rewrite it as 1x cubed, and then the 4x squared, and then the minus 12x, and then the minus 48 equal to 0. So if you're asked to write your function or equation in standard form, you're going to have to take your factored form and then multiply it out, okay? So factored form you stop, standard form multiply it out, all right? I think that is enough for one day. Hopefully it won't be too much for you, and make sure you're getting that quiz done. So the quiz opened up today, and you have until, what did I say, Friday, and that gives you a couple days, Friday by midnight.